Hello everyone, my name is Jerry. Today I want to trace how a 300-year hunt for formulas turned into something deeper. We will see Abel's impossibility result for the quintic and then Galois' explanation for why, which is really the seed of modern abstract algebra. On the bigger picture, how math moved from find a formula to understand the structure. Before we continue, let's start with some historical context and timeline. By the mid-1500s, Cardano had a formula for the cubic, and Ferrari, which is his student, had a formula for quadratic in the same year. In 1770, Lagrange analyzed permutations of roots to explain why those formulas work. Then, in 1824, Abel proved that there's no general radical formula for degree 5. A few years later, Galois reframed the whole question into use groups, the symmetries of the roots to decide when radical formulas can exist. Before Abel and Galois, the goal was very operational. Build explicit expressions from the coefficients using arithmetic and roots, which is what we call radicals. Because degree 2, 3, and 4 had radical solutions, people expected the same trick to keep going. The tension, success up to 4, silence at 5, made the quintic the great open problem for centuries. So what does solvable by radical means? Starting from the coefficient, you reach each root using finitely many addition, subtraction, multiplication, division, and n-nested roots. Here, the quadratic formula is a perfect example. We all know the quadratic formula is negative b plus and minus square root b squared minus 4ac over 2a. In this formula, all we've used is the coefficient from the original general quadratic equation and arithmetic expression, which is addition, subtraction, multiplication, and division, and the square root. So, what about cubic? A much longer one and more complex, but it's still solvable by radicals. Moving on to quadratic. This is only partial of the quadratic expression, yet it's already complex, but it's still solvable by radicals. And as for quintic, Abel's proof proved that it's impossible. Abel's story is short but intense. As a teen, he tightened the binomial theorem beyond Euler's version, and he helped launch the modern theory of elliptic functions. But the headline is 1824. He proves the general quintic is not solvable by radicals. That closes a centuries-long search and raises a new kind of question. If formulas stop at degree 4, what principle explains which equations allow radicals and which don't? Abel worked in poverty and had trouble getting attention in Paris. His big treatise was barely glanced at, so he sent his best work to Sorel's New Berlin Journal. He died of illness at 26. What's more dramatic is that 2 days later, a letter arrived offering him a position in Berlin. Let's take a look at how Abel proved the impossibility of a general formula for the general quintic. let's assume by contradiction that a single radical formula existed for the general quintic and treat that formula as a function of the coefficients. As you move the coefficients around a small loop and return, the nested radicals can only switch among a limited set of branches, just like the graph in the middle. Little flips and small cycles that come from the layers of roots in the expression. But for a generic quintic, if you take the coefficients around certain loops, the five roots gets reshuffled with much richer freedom, like the graph on the right. No fixed nest of radicals can mimic all that shuffling. That mismatch is where the contradiction comes in. Therefore, there's no universal radical formulas for quintics. So about ends, then maybe we just need a smarter formula approach and nudges for mathematics towards concepts. If radicals can't keep up, we need a framework that can explain solvability itself. Enter Galois. He flips perspective. Don't start with expressions, start with symmetries. Take all permutations of the roots that keep every algebraic relation among them true. With composition, those permutations form a group, the Galois group of the polynomial. Now, the key idea is the shape of this group determines whether radicals can possibly work. Galois was a prodigy in a turbulent Paris. Papers lost or rejected, political arrests, and a fatal duel at 20. His ideas were published posthumously, which is part of why the series took time to influence algebra. Picture five seats in a row labeled 1 to 5, with five students sitting in them. These are the five solutions. As you gently change the numbers in the equation and come back, the same five solutions might end up in different seats. Maybe everyone slide one seat to the right, or two students swap seats. Collect all the seat reshuffles that can happen without breaking any algebraic facts. That collection is the equation of symmetry team. Formulas made only from roots, square roots, cubic roots, and so on can simulate only layered, simple reshuffles, like a few steps of swaps and short rotations stacked in stages. If the symmetry team can be built from those simple stages, then a radical formula exists. But for a typical fifth degree equation, allows the full set of seat reshuffles, which is too rich for stacked root operations to replicate. Therefore, Galois' theory successfully explained Abel's proof on why fifth degree doesn't have a general formula. So what are some of the conceptual shift and legacy? Galois' theory relates three views of the same object: the arithmetic of the coefficients, the geometry of the roots, and symmetry group tying them together. That lens explains classical straight edge and compass questions, underpins modern algebra and number theory, and even shows up indirectly in areas like coding, cryptography, where finite fields and groups run the show. While Abel shows a hard stop on there's no general radical formulas for degree 5. Galois explains why by tying solvability to symmetry. Both of them died tragically young, Abel at 26, Galois at 20. If they'd had 20 more years, the 19th century story of analysis and algebra might have been written even earlier. Thank you for listening.